And our next speaker is K.Amelin with the presentation on emergent intelligence and distributed stochastic optimization.
Good afternoon, dear colleagues. I am K.Amelin, and I represent St. Petersburg State University. And I head the Scientific and Design Center on Mathematics, Robotics, and AI. Our center is pretty young, and its main goal is to apply various technologies of robotics and maths and programming in practice. In my presentation, I would like to share with you something about an interesting type of intelligence that is called emergent intelligence. And one of the ways of implementing this emergent intelligence is distributed stochastic optimization. To begin with, I would like to give you the content of what I'm going to talk to you about. First, I will speak about emergent intelligence. That is not a new word, but not many have heard it. I would also like to share with you the technologies that we need to elaborate, and I would like to tell you what we need to work with to transform and use this type of intelligence. And I would like to show you the practical application of this intelligence, so that you can see the results and advantages of implementing this pretty new type of intelligence to carry out some standard and simple tasks that exist now. So, actually, emergent intelligence is the one that exists in a group of single objects, and many know it as a group intelligence or intelligence of a swarm. And one of the examples are ant algorithms, algorithms of work and movement of groups. And now what is actively unraveling is a work of group of pilotless objects that can work in wildly massive groups, in number, I mean. And emergent intelligence turns up when the group itself starts working in a conciliatory manner together. But the main issue that turns up here is when we talk about a large number of nodes, and here I mean thousands and hundreds of thousands of millions of nodes, we face an issue of how will these robots communicate with each other? How will they transmit information between each other? What algorithms should be there inside these robots so that they can do and get this new type of artificial intelligence. Here I show a couple of pictures, and I believe many of you have seen on the internet and in life that actually a flock of birds is pretty simple. But when they work in group, when there is group motion, they can form really impressive figures. Likewise, a group of ants. And interestingly, if we have a look at habitual systems of interaction in a group, like what we're used to doing when mobile devices, for example, interact, when we talk about a large group of robots or how it happens in nature, as a rule, the unit, the robot itself, is pretty simple, with the main task and algorithm that it runs on pretty simple as well. But when they unite in a group, they truly get a new quality. For example, if a flock of birds works, each bird uses pretty easy algorithm. That is, if I am at the edge of the flock, I need to go to the middle, because at the edge of the flock, there is the danger that I will be eaten is higher. And a similar algorithm of interaction with the neighboring units, like again with a flock of birds, it gives the whole flock form and shape, some really beautiful pictures. And to implement in this hard and difficult system group interaction, we need to arrange data transmittance. data exchange. And actually, in conventional standard situations, when we see how robots and computers exchange data, they're usually systems that have one of the chains, that is the so-called core, necessary to transmit information from one node to another. And actually, one of these technologies here is information transmittance along some address. When we have a message with data routing to a certain address so that the nodes can transmit it, route it, and the information is received by the node that we have sent it to. And actually, as for the robot interaction, the central part that enables interaction and data exchange is that element that is actually in the way of fast interaction and fast data exchange. Why is it so? Because when robots begin moving, they change the so-called topology. They change the network itself, and they change the data routing scheme between the robots. Therefore, at the moment when we send data along one robot to some address, this system of routing can change pretty quickly. And it is that environment that the need arises of elaborating new technologies and mechanisms that would enable to communicate well in this system. And actually, we started posing ourselves tasks, and we looked at one task particularly. We need to have a group where robots will communicate only with the neighboring robots. And we have pointed out 4 main layers. That is mathematical support, that is the maths that would enable robots work in this environment, that is algorithmic support. So these are the algorithms that would enable the data exchange. That is also software and hardware that can work in this system. One of the main areas of working in a group is a multi-agent technology. Mathematically speaking, these technologies actually enable work of this network. In multi-agent systems, the core is the agent, and the agent adherent to each element of the group, and the main task of the whole system is the work of these agents and the search of some joint common solution for the whole system through the interaction of this agent and reaching some consensus or some local targets to attain the global goal. Looking at this technology closer, as a rule, at the mathematical level, this system works well, but when we start looking at an ideology of robot interaction in this network, we will see the core, the center, and this network has to have an agent, yellow pages, so that is the same routing as in any network that will hint to the robots which address and how they can connect with which agent through to exchange data. And we have tried this system of implementation on robots. And one of the technologies now is mesh networks that can also work in the so-called changeable, variable topology. But again, in this system, we face the need to route the data, the need to have the center that would enable data exchange. And we have tried this system, and regrettably at low dynamics it works, but when the dynamics is high, robots are moving, the topology is changing fast, and when the modules see only their neighbors, then the mesh network really slows down the speed of change and the speed of data exchange. So what would we like to do? We would like, and we're trying to implement a system that would enable agents to communicate in the network in such a way that every member of the group will send the information to the outer world, to the neighbors, and the group, therefore, changes its structure of the space that it is located in to send the data to the agents. All the other agents that receive this data, that see this data, actually take them and start analyzing them, and therefore drive certain conclusion what the condition and the state of this or that agent is now, to make some management for themselves on the basis of this information. And in this system, topology changes fast, and we are not guided by routing. The question is posed here: what can we apply, mathematically speaking, in the system? And here there are very interesting consensus algorithms. One of them is a local voting protocol that was used initially to computing nodes. So if we have a network of computing nodes, and the links here can be broken, then can be revived, so the topology is variable, and the messages and the load that we have can go not to one center that will distribute the tasks, but will accidentally, randomly go to one of the nodes. And in this situation, when we build a mathematical model in such a way that we have a certain productivity, we have a task queue, we have dynamics characterized by the state at this point of time, and there is a certain function that goes to the next point of time, and our management and our task is to load the system maximally for computing, and we understand that there can be certain lags in computations, and we can see that there can be noise in our measurements. It is also very important for this type of intelligence, because when we exchange information in this kind of system, we receive these things in reality, truly. And our management is comprised of a pretty easy algorithm. That is, every agent looks at the status measured with the lags and with the noise. So it looks at the difference between its status and the status of the neighbors, and estimates and evaluates its control and management to balance it, either to take the message from the neighbors because they are overloaded, or otherwise send them the message if they are underloaded. And we are also adding here another element. If there are a lot of neighbors, we switch on a matrix that enable us to communicate not with all the neighbors, but with part of them. A good example from life is when you want to greet a lot of people in the audience, and you can greet only two people because you have two hands, and your task is to greet everyone. And then you just randomly choose whom you will approach now and whom you will greet and communicate now. So we apply this technology to robots. We have a test bed where we gathered 100 little robots. They're really very silly. They do not know where they're located in the room. They don't know where their neighbors are. They just see obstacles on their way, and their main goal is to move in one direction. And we have light sensors on the robots, and when we switch on a lamp, all the robots should come to this source of light. And interestingly, as soon as we launch one robot, it gets at a very short distance to the obstacle, and it switches on a bypass algorithm. But as soon as we switch on a group and several robots start interacting with their neighbors only, the last robot, without seeing the obstacle, starts bypassing the obstacle in a very good manner. And that is a good example of emergent intelligence. So when a group starts overcoming an obstacle in a more optimal manner than one robot will do. Another interesting task is data routing in a network. When we have cable network with a possibility of breaks. And when we add our element that enables not simply to follow the route of messages from, for example, left nodes to the right node, but when we add an element that each node looks at the neighboring ones and is guided by their load, adding this element, we start loading the whole system in a better and more even way. And in practical implementation in this system, we have sped up data exchange by 10–15%, and that is not a limit we work on. And it shows that our algorithm can additionally not work on itself, but together with the existing solutions. So it is like applied artificial intelligence. Thank you very much for the opportunity to share with you this really interesting topic that is interesting to me. I will be happy to entertain your questions and give you further details. Thank you very much. Konstantin, thank you. And we have received a question right away. Somebody reacted to the word consensus, I believe. So what you are doing, how does it deal with AI in blockchain? It is pretty trendy now. So can blockchain be applied to your work, or can it not? Is what you are doing a more advanced technology? Thank you very much for your question. Actually, usually I answer questions like this in such a manner that blockchain is something that belongs to emergent intelligence. So that is one of the types of practical application thereof. But we can say that we are now getting at trying blockchain technologies. Yes, sure, they can be applied. So answering the question directly, yes, it is very close, but in blockchain there are certain things that can be improved with the technologies that we work on, with adding group work, because blockchain, though it is a distributed system, they have certain centralization that something can be added to. Thank you very much. Thank you. And some more time is left for another question. Do you see a chance for robots to communicate at the level of some language, so that they can be symbolic systems of communication used, like Facebook a couple of years ago and announced that they had 2 bots that elaborated their system of communication. Can emergent intelligence do that? Well, that is an interesting area, because when we work with a group of robots, we think, what should they send each other? What should they exchange? And actually, we send certain property or direction where the robot is now moving at between the robots, but that is not enough. So what naturally occurred to us is certain confidence of where I'm going, and this confidence turned up with emergent intelligence. So they need some more confidence, so to say, that they are moving in the right direction. And on this basis, there can appear a technical layer or level between the nodes of the network that would enable the robots to faster, both locally and globally, transform. And here we can talk about a separate language, I believe, that the user will not see. So the user's main task is to send some message that will go around fast. But very interesting, yes, outcomes can be taken in this respect as well. Thank you very much for this hint. Thank you. Konstantin, thank you.